The nearest star to our Sun is 4.24 light-years away. That is roughly 25 trillion miles. If you launched the fastest outbound spacecraft ever built today, it would arrive in approximately 75,000 years. But that number is not the real problem. The real problem is what happens when you try to solve it. Every proposed fix, faster engines, bigger fuel tanks, generation ships, frozen embryos, creates a new layer of difficulty, more brutal than the one before it. The energy requirements become civilizational. The travel times become biological. The shielding requirements become impossible. And the engineering reliability demanded across decades or centuries has never existed in any machine humans have ever built. Tonight, we confront the possibility that the stars were never ours to reach. If this is the kind of deep science that makes you stop and think, hit like and subscribe. We do not chase trends here. We chase the questions that actually matter. Now, are you comfortable? Let's begin. There is a question that most people never think to ask because the answer seems so obvious, it does not feel like a question at all. How far away is the nearest star? Almost everyone who has taken a basic science class can give you a rough answer. Alpha Centauri, about 4 light-years, maybe 4.3, maybe 4.2, close enough. The number rolls off the tongue easily. 4 light-years. It sounds manageable. It sounds like the kind of distance that belongs on a chart in a classroom, something to memorize for a test and then move on. But that ease, that comfortable familiarity, is the beginning of one of the deepest misunderstandings in all of human thought. Because the phrase 4 light-years is not a number the human brain was built to feel. It is a number the human brain was built to skip past. And the moment you stop skipping and actually try to hold the distance in your mind, something shifts. The comfortable future we have been promised since childhood, the one with starships and colonies orbiting distant suns, begins to look very different. Let us do something that almost no popular science source ever does properly. Let us actually try to feel how far 4.24 light-years is, not as a number, not as a fact, as a distance. Light moves at approximately 186,000 miles per second. In a single second, a beam of light could circle the entire Earth more than 7 times. In 1 minute, it crosses more than 11 million miles. In 1 hour, it covers roughly 670 million miles. And in 1 year, it travels approximately 5.88 trillion miles. That is 1 light-year. The nearest star system, Alpha Centauri, sits at roughly 4.24 times that distance. That gives us a total of approximately 25 trillion miles. Written out in full, that is 25, followed by 12 zeros. It is a number so large that no analogy can make it feel real. But we are going to try anyway, because the failure of the analogy is itself the lesson. Imagine shrinking the sun down to the size of a grain of sand. On that scale, the Earth would be a speck of dust orbiting about an inch away. Mars would be a slightly smaller speck, a little over 1.5 inches out. Jupiter, the giant of our solar system, would sit roughly 5 inches from the grain of sand. Neptune, the outermost major planet, would be about 30 inches away, 2.5 feet. That is the solar system on this scale. Everything humanity has ever visited, every planet our probes have photographed, every moon we have landed on, fits inside a circle smaller than a kitchen table. Now, on this same scale, with the sun as a grain of sand and the entire solar system fitting on a tabletop, how far away is Alpha Centauri? 4.3 miles. Not 4.3 inches. Not 4.3 feet. 4.3 miles. From a grain of sand on your desk to a second grain of sand sitting somewhere across the other side of town, and between them, nothing, no gas stations. No landmarks, no rest stops, just empty space, scaled down, and still incomprehensibly vast. That gap between the edge of the tabletop and the other side of town is the gap that interstellar travel has to cross. And every piece of technology humanity has ever built, every rocket, every probe, every mission that made the front page of every newspaper operated entirely on the tabletop. We have never come close to leaving it. We have never come close to beginning to leave it. This is the first thing people misunderstand about interstellar travel. They look at what humanity has accomplished in space over the last 60 years, and they draw a line forward, assuming the future will simply extend the curve. We went from wooden airplanes to the moon in 66 years. Surely another century or two of progress will carry us to the stars. That reasoning feels natural. It is also completely wrong. And the reason it is wrong has nothing to do with human ambition or creativity. It has to do with the nature of the distance itself. The gap between the Earth and the Moon is about 1.3 light seconds. A beam of light covers it in less than a second and a half. The Apollo missions crossed it in roughly 3 days. The gap between the Earth and Mars, at its closest approach, is roughly 3 light minutes. Our fastest probes have crossed it in about 7 months. The gap between the Earth and the outer planets is measured in light hours. Voyager 2 took 12 years to reach Neptune. Now look at what happens to the numbers when you move from the solar system to the nearest star. The gap jumps from light hours to light years. That is not a linear increase. It is a change of category. It is the difference between walking across a room and walking across a continent. The tools that work for one do not work for the other. You do not cross a continent by taking more steps in the same shoes. You need fundamentally different transportation. And for interstellar distances, that fundamentally different transportation does not exist. It has never existed, and there are serious reasons to believe it may never exist. Here is the most concrete way to understand the problem. Voyager 1, launched in 1977, is the fastest object humanity has ever sent on a trajectory out of the solar system. It is currently traveling at roughly 17 kilometers per second, which is approximately 38,000 miles per hour. It has been flying for nearly 50 years. It has covered about 165 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. That sounds impressive. It is impressive. It represents one of the greatest engineering achievements in human history. And at its current speed, Voyager 1 would reach Alpha Centauri in approximately 75,000 years. 75,000 years. Human civilization in its entirety, from the first permanent settlements in Mesopotamia to this moment, spans roughly 10,000 years. Voyager would need 7.5 times the entire length of recorded human history to reach the nearest star. And it would arrive as a dead, frozen, unpowered piece of metal with no ability to slow down, observe, or transmit data back. It would simply fly through the Alpha Centauri system at 38,000 miles per hour and continue into the void on the other side, unseen and unnoticed, forever. That is the baseline. That is where we actually stand. Every conversation about interstellar travel that does not begin from this baseline is a fantasy dressed in technical language. The history of how we arrived at this misunderstanding is worth examining because it reveals how deeply the illusion runs. In the early 20th century, as the distances to other stars were being measured with increasing precision, the numbers were so large that scientists themselves struggled to convey them to the public. The light year was introduced partly as a convenience, a way to compress trillions of miles into a tidy 2-word phrase, but the compression worked too well. People began treating light years the way they treat miles, as units on a continuous scale that you could simply cross if you had a fast enough vehicle. The science fiction of the 1930s, 40s, and 50s cemented this assumption into popular culture. Writers needed their characters to move between star systems within the span of a story, so they invented warp drives, hyperspace jumps, and faster-than-light travel as casual plot devices. Within a generation, the public came to think of interstellar travel the way previous generations thought about crossing the Atlantic. Difficult, expensive, dangerous, but ultimately just an engineering problem waiting for the right breakthrough. The mid-20th century seemed to confirm this optimism. The nuclear age arrived, and with it came proposals that sounded genuinely plausible. Project Orion, conceived in the late 1950s, proposed a spacecraft propelled by detonating nuclear bombs behind a massive pusher plate. The physics worked. Calculations showed that an Orion ship could theoretically reach several percent of the speed of light, bringing Alpha Centauri within range of a multi-decade voyage rather than a multi-millennial one. Freeman Dyson, one of the most respected physicists alive at the time, worked on the project and believed it was feasible with existing technology. For a brief historical moment, it looked like nuclear propulsion might be the key that opened the galaxy. That optimism was not confined to fiction. It saturated the culture of the space age at every level. In the mid-1960s, as the Apollo program was ramping toward the moon, the physicist Dandridge Cole published a book called Beyond Tomorrow, in which he laid out a timeline for human expansion into the galaxy. By his estimate, interstellar colonization would begin within a few centuries. His reasoning was straightforward. The rate of technological acceleration in the 20th century was so dramatic that projecting it forward made almost anything seem inevitable. Rockets had gone from non-existent to orbital in 50 years. Nuclear energy had gone from theoretical to operational in a decade. Why should the stars be different? This attitude was not fringe, it was mainstream. NASA itself, in its early decades, commissioned studies on interstellar propulsion with the implicit assumption that the problem was solvable on a timeline measured in generations rather than millennia. The British Interplanetary Society, one of the oldest and most respected space advocacy organizations in the world, undertook Project Daedalus in the 1970s as a serious engineering study of an uncrewed interstellar probe. The underlying premise of the entire exercise was that interstellar travel was an engineering problem, not a physics problem. That the laws of nature permitted it, and the only question was how much effort and ingenuity would be required. Television and film cemented this belief into the public consciousness with extraordinary efficiency. Star Trek, which first aired in 1966, presented interstellar travel as routine. The Starship Enterprise moved between star systems in hours or days. The crew visited new worlds every week. The technology was fictional, warp drives and transporters, but the emotional message was real. The stars are reachable. The galaxy is a neighborhood. Exploration is our destiny. Carl Sagan reinforced this narrative from the scientific side. His television series Cosmos, broadcast in 1980, reached hundreds of millions of viewers worldwide and presented the dream of interstellar travel with poetic conviction. Sagan was careful to acknowledge the difficulty, but his framing was always forward-looking. The stars awaited. It was a matter of when, not whether. What none of these voices, fictional or scientific, ever fully communicated was the nature of the gap between solar system travel and interstellar travel. They treated the gap as quantitative, a bigger number, a longer trip, a harder version of the same kind of problem. In reality, the gap is qualitative. It is not that interstellar distances are many times greater than interplanetary distances. It is that interstellar distances change the category of the problem entirely. From engineering to something closer to the limits of physical law, the shift in institutional language over the past 2 decades is itself revealing. NASA's strategic documents in the 1990s and early 2000s occasionally referenced interstellar exploration as a long-term aspiration. By the 2010s, those references had largely disappeared. The agency's current roadmaps focus on the Moon, Mars, and the outer solar system. Interstellar travel is not mentioned as a goal, a target, or even a distant possibility. This silence is not accidental. It reflects a quiet institutional recognition that the problem is not on any foreseeable development timeline. The engineers and physicists who work at the highest levels of space mission planning know something that the public, still marinating in 60 years of Star Trek and Cosmos and optimistic press releases, largely does not. The stars are not the next step. They may not be a step at all. This disconnect between public expectation and professional assessment is one of the most important and least discussed features of the interstellar conversation. The public believes interstellar travel is inevitable because every authority figure they have ever heard on the subject, from Sagan to Hawking to the latest documentary narrator, has told them so. The professionals who would actually have to build the spacecraft have, with increasing honesty and decreasing volume, stopped making that promise. It was not. Project Orion was cancelled in 1965, partly due to the partial nuclear test ban treaty, partly due to cost, and partly because the engineering challenges of building a ship that could survive thousands of nuclear detonations turned out to be far more severe than initial enthusiasm suggested. But the deeper lesson was not about politics or engineering. It was about what the calculations actually showed when you worked through them honestly. Even an Orion ship, using the most energetic propulsion method available in the 1960s, would have required a vessel massing thousands of tons, carrying an enormous number of nuclear charges, sustaining its crew for decades through the most hostile environment imaginable. And that was for a one-way trip. A round trip, or even a mission capable of decelerating at the destination, would multiply the requirements by a factor that pushed the concept from ambitious to absurd. The same pattern has repeated with every subsequent proposal. Fusion drives, antimatter engines, ramjets that scoop hydrogen from the interstellar medium. Each concept offers a theoretical improvement over the last. Each one, when subjected to detailed engineering analysis, reveals a new category of difficulty that the previous concept did not have to face. The proposals get more creative. The difficulties do not get smaller. They get different, and in many cases, they get worse. What makes this pattern so insidious is that it looks like progress from the outside. Every decade, a new paper is published proposing a faster, more elegant propulsion concept. Every decade, the media reports it as a step toward the stars. And every decade, the actual distance between what we can build and what interstellar travel requires remains functionally unchanged. We are not climbing a mountain. We are standing at the base, designing increasingly sophisticated drawings of ladders, and congratulating ourselves on the artistry while the summit remains exactly where it always was. There is a psychological dimension to this that deserves attention because it affects how honestly we can evaluate the problem. Human beings are pattern completion machines. We see a trajectory and we extend it. We went from horse-drawn carriages to automobiles in 50 years. We went from propeller planes to the moon in another 50. The pattern says that in another 50 or 100 years, we will go from the moon to the stars. But this projection commits a fundamental error. It assumes that all distances are the same kind of problem, differing only in degree. They are not. The distance from New York to London is roughly 3,400 miles. The distance from the Earth to the Moon is roughly 240,000 miles. That is a factor of about 70. The distance from the Earth to Mars is roughly 140 million miles at closest approach. That is a factor of about 580 compared to the Moon. Each of these jumps was enormous, and each required a revolution in technology. But the jump from Mars to Alpha Centauri is not a factor of 500 or 5,000 or even 5 million. It is a factor of roughly 160,000 compared to Mars. And that factor does not just mean you need a better engine. It means you need a fundamentally different relationship with energy, time, materials, science, biology, and the continuity of human institutions across timescales that no civilization in history has ever sustained. This is the point where the analogy to ocean crossings and continent crossings breaks down completely and permanently. When Europeans crossed the Atlantic, the ocean was hostile but finite. The ships were slow, but the journey lasted weeks, not centuries. The crews were exposed to danger, but not to the kind of radiation that dismantles DNA at the molecular level. And on the other side, there was air to breathe, water to drink, land to stand on, and an entire biosphere that, however unfamiliar, operated on the same chemistry as the one they left behind. None of those things are true for interstellar space. The medium between the stars is not an ocean. It is a vacuum, with a scattering of hydrogen atoms, roughly 1 per cubic centimeter, interspersed with microscopic dust grains and threaded with cosmic radiation that would slowly kill any unshielded human being aboard any vessel we know how to build. There is no shore on the other side. There is a star, possibly orbited by planets, but those planets may be barren, irradiated, tidally locked, or otherwise utterly unlike anything a human body can survive on. The crossing itself is not weeks or months. At any speed we can currently envision achieving with real engineering, it is decades at minimum and centuries or millennia at worst. The difference between crossing an ocean and crossing interstellar space is not a difference of degree, it is a difference of kind. And failing to recognize that difference is the single largest source of false optimism in the entire conversation about humanity's future among the stars. Let us be precise about what is actually nearby, because even the language of proximity is misleading in this context. The Alpha Centauri system is a triple star system. Alpha Centauri A and Alpha Centauri B orbit each other as a binary pair, and Proxima Centauri, a small red dwarf, orbits the pair at a much greater distance. Proxima Centauri is currently the closest star to our Sun, at approximately 4.24 light-years. It is known to host at least one planet, Proxima Centauri b, which orbits within the star's habitable zone. When this planet was confirmed in 2016, it generated enormous excitement. The nearest star has a planet in the right zone for liquid water. The headlines wrote themselves. But the excitement obscured critical details. Proxima Centauri is a red dwarf, a type of star known for violent flare activity. In 2018, a superflare was observed from Proxima Centauri that was, in certain wavelengths, roughly 100 times more energetic than the most powerful flares recorded from our own Sun. Proxima b orbits so close to its star that it is almost certainly tidally locked, with one hemisphere in permanent daylight and the other in permanent darkness. The radiation environment on its surface, even on a good day, would be punishing by Earth standards. And, on a bad day, during one of Proxima Centauri's frequent flares, the planet's surface would be bathed in ultraviolet and X-ray radiation intense enough to sterilize exposed biology. This is the nearest potentially habitable world, the closest place we could even theoretically go. And reaching it would require crossing 25 trillion miles of vacuum, surviving decades or centuries of cosmic radiation, solving every engineering problem that no one has solved yet, and arriving at a world that might not be habitable at all. The next nearest candidates are even further. Barnard's star is about 6 light-years away. Wolf 359 is roughly 7.9 light-years out. The nearest Sun-like star with confirmed planets in a comfortable habitable zone is considerably further still. Every additional light year multiplies the travel time, the energy requirement, the radiation exposure, the shielding mass, the system reliability demand, and the probability that something critical will fail before arrival. There is a phrase that appears throughout the literature on interstellar travel, used by physicists and engineers who have spent their careers studying the problem. The phrase is the tyranny of the rocket equation. It refers to the fundamental mathematical relationship between the speed you want to reach, the exhaust velocity of your propulsion system, and the amount of fuel you need to carry. The equation is exponential. It does not scale politely. If you want to go twice as fast, you do not need twice as much fuel. You need exponentially more. And if you also need to slow down when you arrive, the fuel requirement roughly squares. For interstellar speeds, the numbers become surreal. A chemically propelled spacecraft, attempting to reach even 1% of light speed, would need to carry a fuel mass so enormous that no known material could contain it and no known structure could support it. This is not a temporary limitation. It is not a gap in current technology that will close with a few more decades of research. The rocket equation is a law of physics. It applies to every propulsion system that works by expelling mass. It applied to the Saturn V. It will apply to whatever we build next. The only way around it is to find a propulsion method that does not carry its own fuel, and every such method proposed so far, laser sails, ramjets, beamed energy, introduces its own set of constraints that are, in many cases, equally severe. The distance between the stars is the silent multiplier behind every problem in interstellar travel. It is the reason the energy requirements are civilizational rather than merely expensive. It is the reason the travel times are biological rather than merely long. It is the reason the shielding demands are prohibitive rather than merely heavy. And it is the reason the reliability requirements are unprecedented rather than merely challenging. Every other problem in interstellar travel, propulsion, energy, radiation, dust, biology, engineering, is made lethal by the distance. Solve any one of them in isolation, and the distance ensures the others will still kill the mission. This is the foundational reality that the rest of this story is built on, not that space is big. Everyone knows space is big. The point is that the specific distance between stars, even the nearest ones, places interstellar travel in a category of difficulty that is separated from everything humanity has ever done by a gap so wide that no incremental progress can bridge it. And the reason that matters is that nearly every public conversation about interstellar travel treats the problem as though incremental progress is enough. Build a slightly better engine, find a slightly lighter material, develop a slightly more efficient power source. Each improvement brings the stars a little closer. That is the story we tell ourselves. It is the story that launch, announcements, and research papers and science fiction have been reinforcing for a century. And it is wrong. Not because the improvements are not real, they are. But because the distance between where those improvements leave us and where we need to be is not a gap that closes gradually. It is a cliff. And we are standing at the bottom looking up. The next part of this story examines what sits at the top of that cliff. The propulsion systems and energy sources that would be required to cross interstellar distances in any meaningful time frame, what they promise, what they actually deliver, and why the most ambitious interstellar propulsion program ever funded was quietly shelved before it achieved a single flight test. Because if you cannot solve the engine problem, the rest of the conversation is academic. And after 60 years of trying, we have not solved it. We have not come close. And the physics suggests we may not be able to. Every conversation about reaching another star eventually arrives at the same hopeful sentence: We just need a better engine. It sounds reasonable. It sounds like the kind of problem engineers solve. History is full of moments where a new propulsion technology shattered a previous speed limit and opened a frontier that had been closed. Sail gave way to steam. Steam gave way to internal combustion. Propellers gave way to jets. Jets gave way to rockets. Each transition seemed impossible before it happened and obvious afterward. Surely interstellar travel is just the next transition in that sequence. A harder version of the same story. It is not. And the reason it is not requires understanding something that most people have never been forced to confront. The problem with interstellar propulsion is not that we lack a clever idea. We have dozens of clever ideas. The problem is that every clever idea, when examined honestly against the physics of the actual distance involved, fails. Not because the idea is bad, but because the universe imposes constraints on propulsion that do not bend, no matter how creative the engineering becomes. Those constraints are not temporary. They are not funding problems. They are features of the physical laws that govern motion, energy, and mass, and they apply to every civilization that has ever existed or ever will exist anywhere in the cosmos. Let us start with what we have now and work our way up. Chemical rockets are the workhorses of the space age. Every crewed mission in history, from Yuri Gagarin's first orbit to the Apollo moon landings to the International Space Station, was launched on chemical propulsion. The principle is simple. You carry a fuel and an oxidizer. You ignite them. The resulting hot gas is expelled at high speed out the back, and Newton's third law pushes the rocket forward. Chemical rockets are powerful, reliable, and well understood. They are also hopelessly, catastrophically inadequate for interstellar travel. The reason is specific and mathematical. The exhaust velocity of a chemical rocket, the speed at which the propellant leaves the nozzle, is roughly 4.5 kilometers per second for the best engines ever built. The speed required to reach Alpha Centauri in any time frame shorter than tens of thousands of years is a significant fraction of the speed of light, which is 300,000 kilometers per second. The gap between 4.5 and 300,000 is not a gap that fuel quantity can bridge. The rocket equation, the fundamental relationship governing all reaction-based propulsion, is exponential. To reach a target velocity much higher than your exhaust velocity, you need an amount of fuel that grows not linearly, but exponentially with every increment of speed. For a chemical rocket attempting to reach even 1% of light speed, 3,000 kilometers per second, the required fuel-to-payload ratio would be so large that the fuel mass would exceed the mass of the observable universe. That is not an exaggeration. That is the mathematics. Freeman Dyson, one of the 20th century's most respected physicists, summarized it bluntly. Chemical fuels are hopeless for interstellar travel, not difficult, not expensive. Hopeless. The next step up is nuclear propulsion. And for a brief window in the middle of the 20th century, nuclear propulsion looked like it might actually work. There were two main concepts. Nuclear thermal propulsion heats a propellant, usually hydrogen, by passing it through a nuclear reactor core. The exhaust velocity is roughly twice that of chemical rockets. Better, but still nowhere near sufficient for interstellar speeds. The concept was tested during the Nerva program in the 1960s, and it worked. Engines were built and fired. But the improvement in exhaust velocity, while meaningful for missions within the solar system, does not change the fundamental calculus for interstellar distances. Doubling the exhaust velocity reduces the fuel ratio, but does not escape the exponential trap. You are still carrying your reaction mass. The rocket equation still applies. The numbers are still impossible. The second nuclear concept was far more ambitious. Project Orion, conceived by Ted Taylor and Freeman Dyson at General Atomics in the late 1950s, proposed propelling a spacecraft by detonating nuclear bombs behind a massive steel pusher plate. Each detonation would slam the plate forward. Springs and shock absorbers would smooth the ride. The effective exhaust velocity of nuclear pulse propulsion was dramatically higher than any chemical or nuclear thermal system, potentially reaching tens of kilometers per second or more, depending on the design. Calculations showed that an Orion vehicle could theoretically reach 3 to 5% of light speed, bringing Alpha Centauri within range of a voyage lasting roughly a century. The physics was sound. Dyson and his team were not dreamers. They were among the best engineers and physicists on the planet, and they believed the concept could be built with 1960s technology. But believing something can be built and actually building it are separated by an ocean of practical reality. An Orion ship, designed for an interstellar mission, would need to be enormous, massing thousands of tons at minimum, carrying tens of thousands of nuclear charges, each precisely engineered and detonated in sequence over decades of continuous operation. The pusher plate would need to survive repeated nuclear blasts at close range without cracking, warping, or ablating away. The shock absorption system would need to function flawlessly through thousands of detonation cycles. The crew would need shielding from the radiation produced by each blast. Shielding so massive it would add yet more weight to a vehicle already straining the limits of any conceivable construction capability. Project Orion was cancelled in 1965. The Partial Nuclear Test Ban Treaty made atmospheric nuclear detonations illegal, which eliminated the possibility of testing. But the treaty was not the real reason Orion died. The real reason was that the gap between a theoretical calculation and a functioning interstellar vehicle was so vast that no credible engineering path connected them. You could write the equations, you could even build small-scale models. But building the actual ship, a vessel capable of surviving a century-long journey through interstellar space, powered by continuous nuclear explosions, was beyond anything that 1960s engineering, or for that matter, 21st century engineering, could deliver. The same pattern holds for fusion propulsion. Fusion, the process that powers the sun, releases far more energy per unit of fuel than fission. A fusion-powered spacecraft could in principle achieve exhaust velocities of several hundred kilometers per second, a substantial improvement over fission systems. Multiple designs have been proposed. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, designed an uncrewed fusion-powered probe capable of reaching Barnard's star, roughly 6 light-years away, in approximately 50 years. The design was serious, detailed, and grounded in physics that was at least theoretically achievable. But theoretically achievable is doing a great deal of work in that sentence. As of today, no fusion reactor on Earth has achieved sustained net energy gain for any practical duration. After more than 70 years of fusion research, consuming tens of billions of dollars across multiple nations, we have not yet built a power plant that runs on fusion, let alone a spaceship engine. The engineering challenges of containing a plasma at 100 million degrees, sustaining the reaction, and extracting useful thrust in a compact, lightweight, reliable package that can operate for decades without maintenance remain unsolved. And even if fusion propulsion were perfected tomorrow, the Daedalus study made clear that the resulting vehicle would be enormous. The Daedalus probe itself would have massed roughly 50,000 tons at launch, most of which was fuel. For a crewed mission, the mass would be orders of magnitude greater. The fusion problem deserves a longer pause because it illustrates something important about the gap between theoretical possibility and practical reality. Controlled nuclear fusion was first proposed as an energy source in the 1950s. The optimism at the time was enormous. Scientists believed a working fusion reactor was 20 years away. That estimate has been repeated, almost verbatim, in every subsequent decade. In the 1970s, fusion was 20 years away. In the 1990s, it was 20 years away. In the 2010s, it was 20 years away. The joke in the physics community, old enough to have grey hair of its own, is that fusion is always 20 years away. This is not because the physicists are incompetent. It is because the engineering challenges of sustaining a controlled fusion reaction are genuinely, stubbornly, extraordinarily hard. The fuel, a plasma of hydrogen isotopes, must be heated to temperatures exceeding 100 million degrees Celsius, roughly 6 times hotter than the core of the Sun. At those temperatures, no physical container can hold the plasma. It must be suspended in a magnetic field of extraordinary precision, shaped and controlled in real time to prevent the plasma from touching the walls of the reactor and instantly cooling below the ignition threshold. The magnetic confinement must be sustained not for microseconds or milliseconds, but for extended periods, long enough for the fusion reactions to produce more energy than is consumed by the heating and confinement systems. As of today, the most advanced fusion experiment in the world is ITER, a multinational project under construction in southern France. ITER is designed to produce 10 times more fusion energy than it consumes, a milestone called Q equals 10. It is not a power plant. It will not generate electricity. It is a physics experiment designed to demonstrate that sustained net energy gain from fusion is achievable. ITER's construction began in 2010. Its first plasma has been repeatedly delayed and is not expected before the mid-2030s at the earliest. Full deuterium-tritium fusion operations are not expected until the mid-2030s. The project has cost over 20 billion euros, with some estimates of the full life cycle cost running considerably higher. Even if ITER succeeds completely, it will demonstrate fusion energy production in a reactor the size of a building, consuming enormous quantities of power for its magnets and support systems, producing a thermal output that must then be converted to electricity through conventional steam turbines. It is a ground-based facility with unlimited access to external power, cooling water, maintenance crews, and replacement parts, translating that achievement into a compact, lightweight, self-contained propulsion system capable of operating autonomously for decades in the vacuum of interstellar space is a leap of engineering so vast that no one working on ITER would describe it as a natural next step. It is more accurately described as a separate revolution, one that would need to follow the fusion energy revolution, which itself has not yet occurred after 70 years of continuous effort. The point is not that fusion propulsion is impossible in principle. It is that the timeline from here to a functioning fusion drive is measured not in decades, but in generations, and that timeline has not been shortening. It has been holding steady or lengthening for the entire history of fusion research. Betting the future of interstellar travel on fusion propulsion is betting on a technology that has been receding into the future at the same rate we have been approaching it. There is a problem that sits beneath every propulsion concept discussed so far, one that is so fundamental it deserves its own examination. Deceleration. Getting a spacecraft up to interstellar speed is only half the problem. If the goal is anything more than a flyby, the spacecraft must also slow down when it arrives. And slowing down is, in terms of energy and propulsion, essentially the same problem as speeding up. You need to cancel the velocity you spent so much energy acquiring. For a rocket-propelled vehicle, this means carrying enough fuel not only to accelerate, but also to decelerate. The rocket equation applies in both directions. The fuel required for deceleration must itself be accelerated during the departure phase, which means the total fuel requirement at launch is not doubled, it is squared. To put this in concrete terms, a spacecraft that requires a fuel-to-payload ratio of 10:1 for acceleration alone would require a ratio of roughly 100:1 for a mission that includes deceleration. For higher-speed missions, where the acceleration ratio is already enormous, the deceleration penalty pushes the total fuel mass into ranges that are not merely impractical but physically absurd. The vehicle becomes almost entirely fuel, with the payload shrinking to a negligible fraction of the total mass. Alternatives to onboard deceleration fuel have been proposed. A magnetic sail, which generates drag against the interstellar medium's magnetic field and charged particle environment, could, in theory, slow a spacecraft over very long distances. But the deceleration rates achievable with a magnetic sail are extremely low, measured in fractions of a millimeter per second squared. Slowing from 10% of light speed to orbital velocity using a magnetic sail would take decades or centuries of additional travel time, extending the mission far beyond the cruise phase itself. Another concept involves pre-positioned laser arrays at the destination, which would fire on the spacecraft's sail as it approaches, providing deceleration thrust. This requires building an interstellar laser facility at the target star before the mission arrives, which presupposes a prior mission to deliver and construct that facility, which faces all the same constraints as the mission it is meant to support. It is a circular solution that moves the problem rather than solving it. Robert Forward, one of the most creative interstellar propulsion theorists of the 20th century, proposed a scheme in which a large light sail would detach a smaller inner sail upon arrival. The outer sail, continuing forward, would reflect the laser beam back onto the inner sail, decelerating it. The geometry is ingenious. The physics is valid. The engineering required to execute it, separating two sails at interstellar distances, precisely aligning a reflected beam across millions of kilometers, and controlling the deceleration of a crewed or robotic vehicle using a beam that has been reflected off a receding sheet of material in deep space, remains far beyond any demonstrated capability. Deceleration is the hidden tax on every interstellar mission concept. It roughly squares the already enormous propulsion requirement. It eliminates most of the faster mission profiles because the fuel penalty at higher speeds becomes catastrophic, and it has no clean solution. Every proposed approach either requires prohibitive fuel mass, impractical pre-positioning of infrastructure, or deceleration timescales so long that they reintroduce the very duration problems the higher speed was meant to avoid. Then there is antimatter. In terms of raw energy density, antimatter is the ultimate fuel. When a particle of matter meets its corresponding antiparticle, they annihilate each other completely, converting 100% of their combined mass into energy. By comparison, nuclear fission converts less than 1% of mass into energy, and fusion converts less than 1% as well, though somewhat more efficiently. Antimatter propulsion, if it could be harnessed, would provide exhaust velocities approaching the speed of light itself. A few kilograms of antimatter, annihilating with an equal mass of normal matter, would release energy equivalent to the largest nuclear weapons ever built. The problem is production. The total amount of antimatter ever produced by all the particle accelerators on Earth combined is measured in nanograms. Producing a single gram of antimatter with current technology would require roughly 25 million billion kilowatt-hours of energy, a figure so large it defies practical interpretation. One frequently cited NASA estimate from the late 1990s put the cost at approximately $62.5 trillion per gram, and no subsequent advance has changed the order of magnitude. And an interstellar mission would require not grams but kilograms or tons. Even if production efficiency improved by a factor of 1 million, which would represent a breakthrough without precedent in the history of technology. The energy required to produce sufficient antimatter would exceed the total energy output of human civilization for years or decades. And storage presents its own nightmare. Antimatter annihilates on contact with any normal matter. It must be suspended in a perfect magnetic vacuum, contained by fields that cannot flicker or fluctuate for the entire duration of the mission. A single failure in containment would not merely end the mission. It would produce an explosion that would destroy the vehicle and everything near it. Antimatter propulsion is not a technology waiting for investment. It is a concept separated from reality by gaps in production, storage, and engineering so large that no plausible development path connects where we are to where we would need to be. It exists in the same category as warp drives and teleportation, permitted by no known law of physics in its pure theoretical form, but blocked by practical constraints so severe that calling it a future technology is more aspiration than prediction. Which brings us to the concept that, until very recently, represented the most credible near-term approach to interstellar travel. Breakthrough Starshot, announced in 2016 by physicist and investor Yuri Milner, alongside cosmologist Stephen Hawking and Facebook founder Mark Zuckerberg. Breakthrough Starshot proposed a radically different approach to the propulsion problem. Instead of carrying fuel, the spacecraft would carry almost nothing at all. The payload would be a gram-scale chip, a star chip, equipped with cameras, sensors, and a communication system, attached to a reflective sail a few meters across and thinner than a human hair. A ground-based array of lasers, generating a combined output of up to 100 gigawatts, would focus a beam on the sail and accelerate it to roughly 20% of the speed of light within minutes. At that speed, the probe would reach Alpha Centauri in approximately 20 years. The concept was elegant. It sidestepped the rocket equation entirely by leaving the energy source on the ground. It avoided the mass problem by shrinking the payload to almost nothing. And it used physics that, at the level of basic principles, was well understood. Light exerts pressure on surfaces. Aim enough light at a thin enough sail, and the sail accelerates. The math checks out. The project received $100 million in initial funding and immediate global attention. For the first time, a serious, well-funded effort was aimed at an actual interstellar mission with a timeline measured in decades rather than centuries. Researchers at institutions including Harvard, Caltech, and the University of California, Santa Barbara began studying the component technologies. Laser phasing, sail materials, communication at interstellar distances, navigation, and the interaction of a relativistic spacecraft with the interstellar medium. The work was real. The physics was grounded. And the problems they uncovered were enormous. The laser array would need to produce 100 gigawatts of coherent, precisely phased light. For reference, 100 gigawatts is roughly the total electrical generating capacity of a mid-sized industrialized nation. The array would need to be built at scale, likely in a remote desert location, covering an area of roughly 1 square kilometer. The individual lasers would need to be phase-locked with nanometer precision across that entire area, a technical challenge that laboratory demonstrations have addressed with tens of lasers, but that scales to millions. The sail itself would need to survive the initial acceleration, which involves absorbing terajoules of energy in minutes without melting, deforming, or losing reflectivity. The material constraints are severe. The sail must be highly reflective at the laser wavelength, extremely lightweight, and capable of maintaining structural integrity under acceleration forces of thousands of times Earth's gravity. Then, there are the problems that emerge during the cruise phase. At 20% of light speed, the starship would cross the interstellar medium in roughly 20 years. During that time, every atom of hydrogen, every microscopic dust grain in its path, would impact the sail and chip at relativistic velocity. Research published by teams including physicists at Harvard found that gas bombardment at this speed would erode the spacecraft's surface, creating damaged tracks in the material. Dust grain impacts, even from particles smaller than a grain of sand, would carry kinetic energies equivalent to small explosions. Dust grains in the interstellar medium, even those far too small to see, would strike the sail and chip with energies sufficient to erode and crater the surface over the course of the journey. The cumulative damage would require some form of shielding, but shielding adds mass, and mass is the one thing a gram-scale spacecraft cannot afford. Communication presents yet another barrier. The starship would need to transmit data back to Earth from 4 light-years away, using a power source that fits on a chip weighing a few grams. The signal would take more than 4 years to arrive. Even with the laser array repurposed as a receiving antenna, the data rate would be agonizingly slow, and the likelihood of successfully detecting the signal against the noise background of deep space is uncertain. And then there is deceleration. The Breakthrough Starshot concept is a flyby mission. The starship does not slow down. It screams through the Alpha Centauri system at 20% of light speed, capturing whatever data its instruments can gather during the brief window when it is close enough for useful observations, and then continues into interstellar space forever. It does not enter orbit, it does not land, it does not return. The entire scientific output of a mission lasting 2 decades and costing billions of dollars would be a few hours of data collected during a high-speed flyby of a star system 4 light-years away. Despite all of this, Breakthrough Starshot was the most serious interstellar effort ever funded, and in September 2025, Scientific American reported that the project had been placed on indefinite hold. Of the $100 million pledged, roughly $4.5 million had been spent across approximately 30 research contracts over 9 years. The project's executive director had moved on. The advisory board chair had shifted focus. No final report had been published. No prototype had been built. No laser had been fired at a sail in anything resembling a flight test. The most credible interstellar propulsion program in history ended not with a technical failure or a dramatic cancellation, but with a quiet fade into uncertainty. Researchers described the outcome not as a failure of will, but as a confrontation with the sheer scale of the engineering required. The problems were not unsolvable in principle. They were unsolvable at any cost or timeline that a single private foundation could sustain. This is the pattern that defines interstellar propulsion. The ideas are brilliant, the physics is often sound, and the engineering is always, without exception, beyond anything that exists or is plausibly on the horizon. There is one more concept that deserves examination because it is the one most frequently cited by people who believe the laws of physics will eventually yield to human ingenuity: the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre published a paper showing that general relativity, Einstein's theory of gravity, technically permits a geometry of space-time in which a bubble of flat space moves faster than light by contracting the space ahead of it and expanding the space behind it. A spacecraft inside the bubble would not itself be moving faster than light relative to its local space-time. The space-time itself would be doing the moving. The concept attracted enormous attention and has since spawned hundreds of follow-up papers exploring variations, refinements, and alternative geometries. The problem is what the mathematics requires to make it work. The original Alcubierre drive demands a form of matter with negative energy density, sometimes called exotic matter. No such matter has ever been observed. No physical theory predicts that it can exist in the quantities required. The energy needed to create and sustain a warp bubble, even in the most optimized later versions of the concept, is measured in quantities comparable to the mass energy of entire planets or stars. Some revised models have reduced the energy requirement substantially, but even the most favorable estimates remain far beyond anything any civilization could plausibly generate. More fundamentally, the Alcubierre drive is not a technology. It is a mathematical solution to a set of equations. The equations of general relativity permit many solutions that do not correspond to anything physically realizable, including closed time-like curves, which are solutions that describe time travel. The fact that the equations allow a particular geometry does not mean that geometry can be created, sustained, or controlled. No experiment has ever produced even a microscopic warp bubble. No known mechanism exists for generating negative energy density at macroscopic scales. The Alcubierre drive remains, as it has for 3 decades, a fascinating mathematical curiosity with no connection to experimental physics or engineering. This is worth emphasizing because the warp drive occupies an outsized place in the public imagination. It is the escape hatch, the get-out-of-physics-free card. When every other propulsion concept fails, someone inevitably says, "But what about warp drives?" The answer is that warp drives are to interstellar travel what perpetual motion machines are to energy production. They are not forbidden by a specific law of physics in the narrow sense, but they require conditions that no one has any idea how to create, and that may not be possible in the universe as it actually exists. Let us step back and look at the full landscape. Chemical rockets cannot reach interstellar speeds. Nuclear thermal propulsion cannot reach interstellar speeds. Nuclear pulse propulsion could theoretically reach a few % of light speed, but requires a vehicle so massive and an engineering effort so prolonged that no credible path to construction exists. Fusion propulsion remains undemonstrated even for power generation, let alone spaceflight. Antimatter propulsion requires fuel production on a scale that would consume the energy output of entire civilizations for years. Laser sail propulsion works for gram-scale probes on flyby trajectories, but cannot decelerate, cannot carry meaningful payloads, and was shelved before reaching the prototype stage. And warp drives exist only as mathematical solutions to equations with no experimental basis and no known mechanism for realization. Each of these concepts addresses one piece of the problem. None of them addresses all the pieces simultaneously, and interstellar travel requires all the pieces to work together. You need enough speed to cross the distance in a time frame shorter than geological. You need enough energy to achieve that speed. You need a way to carry or receive that energy without the mass penalty destroying the mission. You need to decelerate at the destination if you want to do anything other than fly through at killing speed. You need your propulsion system to operate reliably for decades or centuries without maintenance. And you need all of this to function in an environment where the interstellar medium is actively eroding your vehicle and cosmic radiation is degrading your electronics and your crew. No proposed system satisfies all of these requirements. No combination of proposed systems satisfies all of these requirements, and the constraints are not engineering problems awaiting better funding. They are physical limits imposed by the relationship between energy, mass, distance, and time. The rocket equation does not care about human ambition. The speed of light does not negotiate. The energy density of available fuels is set by nuclear and atomic physics, not by the creativity of engineers. This is the second layer of the argument. The first layer of this argument established that the distance is not merely large, but categorically different from any distance humanity has ever crossed. This layer establishes that the propulsion systems required to cross that distance do not exist, that every proposed system falls short of what is needed, and that the gaps are not closing in any meaningful way. The trajectory of progress in interstellar propulsion over the last 60 years is not a curve approaching a solution. It is a series of proposals, each revealing a new dimension of the problem that the previous proposal did not address. But propulsion and energy are only the beginning. Because even if someone, somewhere, somehow solved the engine problem tomorrow, handed humanity a propulsion system capable of reaching 10 or 20% of light speed with a payload large enough to be useful, the mission would still face a gauntlet of hazards so severe that survival to the destination is not assured and may not even be probable. The space between the stars is not empty, it is not safe, and it does not forgive mistakes. What waits in that space, and what it does to machines and human bodies over decades of exposure, is the subject of what comes next. Imagine you have solved the engine problem. Some unspecified breakthrough has delivered a propulsion system capable of accelerating a spacecraft to 10% of the speed of light, 30,000 kilometers per second, fast enough to reach Alpha Centauri in roughly 42 years. The fuel question is answered, the energy is available, the acceleration phase works. The ship is moving. Now the real problems begin. Because the engine was never the only obstacle. It was merely the most obvious one. The one that attracted the most attention because it was the most tangible, the most amenable to diagrams and equations and hopeful press releases. Behind it, quieter and in many ways more lethal, stand a series of challenges that do not yield to a single breakthrough. They do not compress into a clever engineering solution. They accumulate across time and distance, each one compounding the others, until the probability of mission success drops not gradually, but catastrophically. The interstellar medium is not empty. This is stated in every textbook and ignored in almost every popular account of star travel. Between the stars, there exists a thin but continuous distribution of matter. Hydrogen atoms, averaging roughly 1 per cubic centimeter across the general interstellar medium, though the local region surrounding our solar system is somewhat less dense, at roughly 1/10 to 1/3 of that figure. Helium atoms at roughly 10% of that density, along with trace quantities of heavier elements scattered among the hydrogen and dust. Microscopic grains of silicate and carbonaceous material, remnants of ancient stellar winds and supernova explosions, distributed at a density of roughly a few hundred to a few thousand grains per cubic kilometer. At rest, or at the speeds of conventional spacecraft, this material is negligible. Voyager 1 passes through it without consequence. But at 10% of the speed of light, the physics changes completely. Every atom, every grain, every particle in the path of the spacecraft is no longer a passive mote floating in the void. It is a projectile. And the energy it carries upon impact is determined not by its tiny mass, but by the square of the velocity, which at relativistic speeds becomes enormous. Consider a single hydrogen atom. Its mass is approximately 1.7 times 10 to the negative 27 kilograms, essentially nothing. But at 10% of light speed, that atom strikes the leading surface of the spacecraft with a kinetic energy equivalent to that of a slow-moving bullet, concentrated into a space smaller than an atom. Each impact deposits energy into the spacecraft's surface material, creating a damage track, a narrow column of disrupted molecular structure driven into the hull like a needle into clay. A single impact is insignificant. But over a journey of 4.24 light-years, the spacecraft sweeps through a column of interstellar gas containing approximately 2 times 10 to the 18 hydrogen atoms per square centimeter of frontal area. That is 2 quintillion impacts on every square centimeter of the forward-facing surface. Research conducted for the Breakthrough Starshot program by astrophysicist Team Hoang and colleagues quantified this effect in detail. They found that for quartz-based materials, gas bombardment at 20% of light speed could damage the surface to a depth of roughly 1/10 of a millimeter across the full distance to Alpha Centauri. For graphite, the effect was less severe but still measurable. These numbers apply to a gram-scale probe traveling for 20 years. For a larger spacecraft, traveling at 10% of light speed for 42 years, the exposure is different in detail, but comparable in principle. The surface erodes, the material degrades. And this is just from individual atoms. Dust grains are far worse. A silicate grain measuring 1/10 of a micron in diameter, roughly 1,000th the width of a human hair, contains tens of millions of atoms. At 10% of light speed, such a grain carries kinetic energy equivalent to a small explosive charge. Upon impact, it does not bounce. It does not embed itself. It vaporizes on contact, along with a portion of the spacecraft's hull surrounding the impact point, creating a superheated crater that melts and ejects material in all directions. The resulting damage extends far beyond the volume of the original grain. Each impact is a miniature explosion on the spacecraft's skin. Over 4 light-years, a spacecraft presenting a frontal area of just 1 square meter would encounter thousands of such grains. Some estimates suggest tens of thousands, depending on the density of the interstellar medium along the specific trajectory. Each one leaves a crater. Each crater weakens the structural integrity of the hull. Cumulatively, the surface of the spacecraft is being sandblasted by relativistic shrapnel for decades. The shielding problem that emerges from this is not subtle. You need a forward-facing shield thick enough and tough enough to absorb decades of continuous bombardment without failing. The material must have a high melting point, high tensile strength, and low density to minimize the mass penalty. Graphite and advanced carbon composites are among the best candidates. But even optimistic calculations suggest that a shield capable of protecting a spacecraft over a 4 light-year journey at 10% of light speed would need to be at least several centimeters thick, possibly more, and would itself be partially consumed by the journey. For a large crewed vessel, the shield mass becomes a significant fraction of the total vehicle mass, which feeds directly back into the propulsion problem. Heavier ship, more fuel. More fuel means heavier ship. The same mass spiral that makes propulsion so difficult reasserts itself through the shielding requirement. And dust is not the only threat waiting in the dark between the stars. Cosmic radiation is the silent killer of interstellar travel. On Earth, we are shielded from the worst of it by 2 layers of protection. The magnetosphere, generated by the planet's liquid iron core, deflects the majority of charged particles streaming from the Sun and from beyond the solar system. The atmosphere, equivalent in shielding to roughly 10 meters of water, absorbs most of what gets through. Together, these 2 barriers reduce the radiation dose at the surface to levels that biological life can tolerate. In interstellar space, both barriers are gone. Galactic cosmic rays are high-energy particles, primarily protons and heavier atomic nuclei, accelerated to near-light speeds by supernova remnants, neutron stars, and other violent astrophysical events. They permeate the galaxy uniformly. There is no region of interstellar space that is free of them. Their energies range from modest to staggering, with some individual particles carrying as much kinetic energy as a professionally thrown baseball, compressed into a single atomic nucleus. These particles pass through conventional spacecraft materials like bullets through paper. Aluminum, the standard material for spacecraft hulls, provides minimal attenuation. In fact, When a high-energy cosmic ray strikes an aluminum nucleus, it can produce a shower of secondary particles, neutrons, pions, and gamma rays that are in some ways more biologically damaging than the original particle. This is called secondary radiation production, and it means that adding a thin layer of conventional shielding can actually make the radiation environment inside the spacecraft worse rather than better. Effective shielding against galactic cosmic rays requires mass, a great deal of mass. Water is one of the best general-purpose radiation shields because hydrogen nuclei are effective at absorbing neutrons and slowing charged particles. Calculations suggest that a water shield, roughly 2 to 3 meters thick, would reduce the cosmic ray dose inside a spacecraft to levels comparable to the natural background on Earth's surface. That sounds manageable until you calculate the mass. A water shield 2 meters thick surrounding a habitable volume large enough for a small crew would weigh thousands of tons, tens of thousands, depending on the size of the vessel. And every ton of shielding is a ton that must be accelerated to interstellar velocity and decelerated at the destination, driving the fuel requirement upward in the exponential spiral of the rocket equation. There are lighter shielding materials. Polyethylene, which is rich in hydrogen, provides better protection per unit mass than water. Advanced composite materials, incorporating hydrogen-rich polymers, have been studied by NASA for deep space radiation protection. Active shielding concepts, using powerful magnetic fields to deflect charged particles before they reach the hull, have been proposed. But magnetic shielding effective against the highest energy cosmic rays would require field strengths so enormous that the power and mass requirements rival those of the passive shielding it is meant to replace. And no magnetic field can deflect uncharged particles, like neutrons, which are among the most biologically dangerous components of the secondary radiation environment. The biological consequences of unshielded or inadequately shielded cosmic ray exposure are severe and well documented. DNA damage accumulates with exposure. The body's repair mechanisms can handle a limited rate of damage, but sustained exposure overwhelms them. Cancer risk increases dramatically. The central nervous system is particularly vulnerable. Studies on animal models exposed to simulated cosmic ray environments have shown measurable cognitive decline, including impaired memory, reduced decision-making ability, and behavioral changes. These effects are not hypothetical. They are observed in laboratory conditions designed to approximate the radiation environment of deep space. For a 42-year mission at 10% of light speed, the cumulative radiation dose to an inadequately shielded crew would be measured in sieverts, well above the threshold for significantly elevated cancer risk, organ damage, and central nervous system degradation. The crew that arrives at Alpha Centauri, if they arrive at all, may be neurologically compromised, physically debilitated, and carrying radiation-induced diseases that no onboard medical system could treat. The specific effects of galactic cosmic rays on the human brain have been studied with increasing urgency over the past decade. Driven by NASA's interest in deep space crewed missions to Mars and beyond, the results are not reassuring. In a series of experiments conducted at the NASA Space Radiation Laboratory at Brookhaven National Laboratory, researchers exposed rodents to beams of high-energy charged particles designed to simulate the galactic cosmic ray environment. The particles used included iron ions, silicon ions, and other heavy nuclei, the same species that dominate the biologically damaging component of the cosmic ray flux. The findings were consistent across multiple studies. Rodents exposed to doses equivalent to those a crew would accumulate during a multi-year deep space mission showed measurable cognitive impairment. Specifically, they exhibited reduced performance on tests of learning and memory, decreased ability to distinguish between novel and familiar objects, and increased anxiety-like behavior. Neuroimaging revealed structural changes in the prefrontal cortex and hippocampus, regions critical for decision-making, spatial navigation, and memory formation. The damage was not temporary. Follow-up studies showed that cognitive deficits persisted for months after exposure, with no evidence of recovery. The mechanism is particularly insidious. Unlike low-energy radiation, which primarily damages DNA and can be partially repaired by the body's molecular repair systems, high-energy heavy ions produce dense columns of ionization along their tracks through tissue. When such a particle passes through a neuron, it can destroy the dendritic spines, the tiny protrusions that form synaptic connections between brain cells. The loss of dendritic spines reduces the brain's connectivity, impairing its ability to process information, form memories, and regulate behavior. The effect is cumulative. Each particle that passes through the brain removes a small number of connections. Over years of continuous exposure, the aggregate loss becomes significant. Astronaut health data from the International Space Station provides some corroborating evidence. Though the ISS orbits within the protection of Earth's magnetosphere and therefore experiences a much lower cosmic ray dose than a deep space mission would encounter. Even so, astronauts returning from 6-month ISS missions have reported cognitive changes, including difficulty concentrating and a phenomenon informally known as space fog. Whether these effects are caused by radiation, microgravity, sleep disruption, or some combination remains under investigation. But the direction of the evidence is consistent. The space environment degrades cognitive function, and the degradation worsens with dose and duration. For a 42-year interstellar mission, the cumulative radiation dose to an inadequately shielded crew would far exceed anything studied in the laboratory or experienced by ISS astronauts. The crew that arrives at the destination might retain their technical knowledge but suffer from impaired judgment, reduced problem-solving ability, and emotional dysregulation, precisely the cognitive functions most critical for navigating the challenges of arrival at an unfamiliar star system. Biosphere Two deserves a closer examination because it is the single best real-world test of the concept that underlies every generation ship proposal. Built in the late 1980s in the Arizona desert, Biosphere Two was a 3.14-acre sealed glass structure containing multiple biomes, a rainforest, an ocean with a coral reef, a mangrove wetland, a savanna, and a desert, along with an agricultural wing designed to feed the 8 crew members sealed inside. The project was well-funded, carefully designed, and staffed by dedicated and highly motivated participants. It was intended to operate as a fully closed ecological system, recycling all air, water, and nutrients internally, with no exchange of materials with the outside environment. The first mission, sealed in September 1991, began to fail almost immediately. Oxygen levels dropped steadily, eventually falling from the normal 21% to roughly 14%, equivalent to the atmosphere at an altitude of roughly 13,500 feet. The cause was traced to soil microorganisms consuming oxygen at a higher rate than the plants could produce it, compounded by oxygen reacting with exposed concrete in the structure. Carbon dioxide levels fluctuated wildly. Crop yields were insufficient to feed the crew, who lost significant weight. Pollinating insects died out, threatening the agricultural system. Cockroach and ant populations exploded. Morning glories and other vining plants invaded the rainforest biome, smothering other species. The coral reef declined. Twice during the first mission, outside air was pumped in to raise the oxygen level. Food supplies were smuggled in through an airlock. The crew split into factions. Morale collapsed. By the end of the 2-year mission, Biosphere Two had demonstrated conclusively that a closed ecological system of that scale, designed and maintained by some of the best ecologists and engineers available, could not sustain 8 human beings for 24 months without external intervention. The second mission, begun in March 1994, was terminated after 6 months due to internal disputes and management failures. No subsequent sealed mission has been attempted at comparable scale. The lesson of Biosphere Two is not that closed ecosystems are theoretically impossible. It is that the practical complexity of maintaining a self-sustaining biosphere is so far beyond current capability that even the most ambitious and well-funded attempt failed rapidly and comprehensively. A generation ship would need to accomplish what Biosphere Two could not, but in a much smaller volume, in a much harsher environment, with no possibility of outside intervention, for a duration measured not in months, but in centuries. The gap between what Biosphere Two achieved and what a generation ship would require is not a gap that incremental improvement can bridge. It is a gap that requires a revolution in ecological engineering that has not occurred and shows no signs of occurring, and this assumes no solar particle events from the departure star, no passage through regions of enhanced interstellar radiation density, and no secondary exposure from the ship's own nuclear propulsion system if it uses one. Radiation and dust are the environmental hazards. They are the price of moving through interstellar space at speed, but there is another category of risk that is, in some ways, more fundamental. It does not come from outside the ship. It comes from the ship itself. No machine in human history has operated continuously without maintenance for 42 years. The longest operating spacecraft, Voyager 1 and Voyager 2, have been functioning for nearly 50 years, which is a remarkable achievement. But functioning is a generous term. Both Voyagers have experienced multiple instrument failures. Their power output has declined steadily as their radioisotope thermoelectric generators decay. Several of their science instruments have been shut down permanently. Their onboard computers, built with 1970s technology, have limited processing power and memory. They cannot repair themselves. They cannot replace failed components. They are slowly dying, and the only reason they are still transmitting useful data is that their mission requirements are extraordinarily modest by the standards of an interstellar voyage. They need to measure fields and particles and transmit a thin stream of data at very low bit rates. An interstellar mission, whether crewed or robotic, would demand orders of magnitude more from its onboard systems. Life support systems for a crewed vessel would need to recycle air, water, and nutrients in a closed loop for decades. The International Space Station, the most sophisticated partially closed-loop life support system ever built, requires regular resupply from Earth and constant maintenance by its crew. Components fail. Filters clog, seals degrade, pumps wear out. Biological systems, algae tanks, plant growth chambers, and water recycling units are sensitive to contamination and require monitoring and intervention. On the space station, a failed component can be replaced with a spare launched from Earth on the next resupply mission. On an interstellar ship, there is no resupply. There is no next mission. Every component must either last for the entire journey, be repairable with onboard resources, or be redundant to a degree that no engineering project has ever achieved. The mathematics of redundancy are unforgiving. If a critical system has a 99% probability of surviving 1 year of operation, it sounds nearly perfect. Over 42 years, that 99% annual reliability translates to a cumulative probability of survival of approximately 66%, a 1 in 3 chance of failure. If you need 10 such systems to all function for the entire journey, the probability of all 10 surviving drops to approximately 1.5%. A 98.5% chance that at least one critical system fails. Adding redundancy helps, but redundancy adds mass, complexity, and its own failure modes. Redundant systems must be switched in when primary systems fail. The switching mechanisms themselves can fail. The diagnostic systems that detect failures can fail. Each layer of protection introduces its own layer of vulnerability. This is not pessimism. This is reliability engineering, the branch of engineering that calculates how likely complex systems are to function over time. And the conclusion from reliability engineering is consistent and stark. The probability of a complex crewed spacecraft functioning without catastrophic failure for multiple decades in an environment where no repair or resupply is possible is extremely low unless the vessel is built to standards of robustness and redundancy far beyond anything that has ever been attempted. For a robotic probe, the reliability problem is somewhat less severe because the consequences of partial failure are less catastrophic. A probe that loses one of its cameras can still transmit data from the others. A probe that loses half its power supply can still operate at reduced capacity, but a probe that loses its communication system is dead. A probe that loses its navigation system cannot aim its antenna at Earth. A probe that loses its computer cannot process data or execute commands. And over a 42-year cruise, with no external support of any kind, now layer the radiation problem on top of the reliability problem. Cosmic rays do not only damage biological tissue, they damage electronics. High-energy particles passing through a microprocessor can flip bits in memory, corrupt data, and cause software crashes. This phenomenon, called a single-event upset, is well documented in satellite operations. Spacecraft in Earth orbit experience these events regularly and are designed to recover from them through error-correcting memory, watchdog timers, and hardened circuit designs. But radiation hardening adds mass and reduces performance. The electronics on an interstellar probe would need to be hardened far beyond current standards, and even then, the cumulative dose of decades of cosmic ray exposure would gradually degrade the semiconductor materials themselves, reducing performance and eventually causing permanent failure. This is the convergence that makes interstellar travel so different from any engineering project humanity has undertaken. The hazards are not independent. They interact. Radiation damages the electronics that control the life support systems. Dust erosion weakens the hull that shields the crew from radiation. System failures in propulsion reduce the ability to maneuver or decelerate, extending the mission duration, which increases the radiation exposure and the dust impact count, which increases the probability of further system failures. Each problem feeds the others. The mission does not face a list of separate challenges. It faces a web of interlocking failures, each one making the others more likely and more severe. And we have not yet discussed the most ambitious concept of all, the one that attempts to solve the time problem not by going faster but by accepting the journey will take longer than any human lifetime. Generation ships are the idea that refuses to die. The concept is simple in principle. If you cannot cross the distance between stars in one human lifetime, build a ship large enough to sustain a self-reproducing community across multiple generations. The people who launch the ship are not the people who arrive. Their children arrive, or their grandchildren, or their descendants, many generations removed. The ship becomes a world unto itself, a sealed ecosystem carrying a human population through the void for centuries. The concept has been explored in science fiction since the early 20th century and has been studied with varying degrees of seriousness by engineers and sociologists. The challenges it faces are not primarily technical, though the technical challenges are enormous. They are biological, sociological, genetic, and political. And they are in many ways harder to solve than the engineering. Start with the biological. A generation ship must sustain a human population large enough to avoid genetic bottleneck effects across centuries of isolation. Population genetics research suggests that a minimum viable population for long-term genetic health is somewhere between 160 and several thousand individuals, depending on the assumptions used. The lower estimates assume carefully managed breeding programs designed to maximize genetic diversity. The higher estimates assume natural reproduction without intervention. Either way, the ship must carry at minimum hundreds of people, along with all the food production, water recycling, atmosphere management, and medical infrastructure required to keep them alive and healthy indefinitely. No closed-loop life support system capable of sustaining even a single human being for more than a few years has ever been demonstrated. Biosphere Two, the most ambitious attempt to create a sealed, self-sustaining ecosystem on Earth, failed within 2 years. Oxygen levels dropped, carbon dioxide spiked, crop yields were insufficient, insect populations collapsed. The system was far larger and far better resourced than anything that could be built into a spacecraft, and it could not maintain equilibrium. Scaling that concept down to fit inside a vehicle while simultaneously hardening it against radiation, dust erosion, and system degradation over centuries is a challenge for which no credible engineering path exists. Then there are the sociological problems. A generation ship is not just a vehicle, it is a society. A closed, isolated, involuntary society with no exit and no external input for centuries. The people born on the ship did not choose to be there. They did not volunteer for the mission. They were born into a metal world with no sky, no horizon, no seasons, and no possibility of leaving. Every aspect of their lives, their food, their air, their social structure, their reproductive choices, is dictated by the requirements of the mission. History offers no precedent for a healthy human society operating under these conditions. Every long-duration isolation study ever conducted, submarine deployments, Antarctic winter overstations, the Mars 500 simulation, has documented significant psychological deterioration, interpersonal conflict, and institutional breakdown within months to a few years. Extrapolating these findings across centuries is speculative by definition, but the direction of the extrapolation is not encouraging. The probability of a generation ship maintaining social cohesion, institutional continuity, and mission focus across 10 or 20 or 50 generations, while confined in a sealed environment with no possibility of rescue or resupply, is not a number that any social scientist has been willing to estimate with confidence. There is also the political problem. Who governs the ship? How are decisions made? How are conflicts resolved? What happens when a faction decides the mission is pointless and wants to turn back? What happens when resources become scarce and rationing is required? What happens when the population grows beyond the ship's carrying capacity or shrinks below the minimum viable threshold? These are not hypothetical questions. They are the inevitable consequences of confining a human society in a closed system for centuries. Every political system ever devised by human beings has operated with the assumption that the people within it can, in principle, leave. A generation ship removes that assumption entirely. The implications are profound and deeply troubling, and beneath all of these challenges lies a question that is almost never asked in popular accounts of generation ships. Why would anyone do it? The people who launch the ship will never see the destination. The people who arrive will never have known the world that launched them. The mission itself, crossing the void between two stars, produces no economic return, no strategic advantage, no immediate benefit to anyone. It is a project undertaken purely for the species-level goal of reaching another star. And sustaining a species-level goal across centuries of institutional continuity, generational turnover, and social evolution is something that no human civilization has ever accomplished. The longest continuously operating institutions on Earth, certain religious organizations and universities, have survived for roughly 1,000 years, and they have done so with the enormous advantage of being embedded in a larger society that provides resources, recruits, and purpose. A generation ship has no larger society. It is the society. And the odds of that society maintaining coherence and purpose across the timescales required are, by any honest assessment, very low. The generation ship is not a solution. It is a restatement of the problem in biological and sociological terms. It replaces the question, how do we cross the distance, with the question, how do we sustain a civilization in a sealed container for centuries? And the second question may be even harder than the first. This is the gauntlet. Not one obstacle, but a chain of them, each linked to the next, each made worse by the others. Dust erodes the ship. Radiation degrades the crew and the electronics. System failures accumulate with no possibility of repair. Life support demands a closed-loop ecosystem that has never been demonstrated. And the passage of time, the raw duration of decades or centuries in transit, turns manageable risks into near certainties and engineering challenges into civilizational ones. The engine was never the only problem. It was not even the hardest problem. The hardest problem is the space between departure and arrival, the years and decades and centuries where everything must work, nothing can be replaced, and the universe is actively trying to destroy the mission through radiation, erosion, and the quiet accumulation of mechanical failure. And the most unsettling realization of all is that these problems do not stand in a line, waiting to be solved one at a time. They stand in a circle, each one reinforcing the others. Solving the propulsion problem increases the speed, which increases the dust damage, which increases the shielding mass, which increases the fuel requirement, which makes the propulsion problem harder. Extending the mission duration to reduce speed reduces the dust damage, but increases the radiation exposure, the system reliability demand, and the biological and sociological burden. Every solution creates a new constraint. Every fix shifts the weight to a different point in the structure. And the structure, taken as a whole, may not be able to bear the combined load. What that combined load actually looks like, and what it means for the deepest human assumption about our future among the stars, is where this story ends. Everything described so far has been presented as a sequence. Distance first, then propulsion, then the hazards of the crossing. That sequence is useful for understanding each problem individually, but it is misleading in one critical way. It implies the problems are separate, that they stand in a row like hurdles on a track, and if you clear each one, the race is won. They do not. They form a system, and the behavior of the system is not the sum of its parts. It is the product. This distinction matters more than anything else in this story, because when you add the problems together, interstellar travel looks extraordinarily difficult. When you multiply them, when you see how each one amplifies the others, interstellar travel begins to look like something else entirely. It begins to look like a project that may exceed the outer boundary of what beings like us can accomplish within the physics of the universe we actually inhabit. Let us build the full picture one final time. Not as a list of obstacles, but as a single integrated structure showing how each constraint feeds into every other. Start with distance. The nearest star is 4.24 light-years away. 25 trillion miles. That distance is the multiplier that makes every other variable lethal. If Alpha Centauri were 100 times closer, interstellar travel would be merely extraordinary. At its actual distance, It is something qualitatively different. The distance determines the minimum travel time, which determines the minimum duration of radiation exposure, dust bombardment, system operation, life support function, and institutional continuity required. Every other constraint in this analysis derives its severity from the distance. Reduce the distance and the problems become manageable. At the actual distance, they may not be. Now, add propulsion. No existing or plausibly near-term propulsion system can accelerate a meaningful payload to a significant fraction of light speed. Chemical rockets are ruled out by the rocket equation. Nuclear thermal propulsion offers marginal improvement. Nuclear pulse propulsion is theoretically capable, but requires a vehicle so massive and a construction effort so prolonged that no credible path to realization exists. Fusion propulsion remains undemonstrated for power generation, let alone spaceflight. Antimatter propulsion requires fuel production on a scale that would consume civilizational energy budgets for decades. Laser sail propulsion works for gram-scale flyby probes, but cannot decelerate, cannot carry crews, and has been placed on indefinite hold. And warp drives remain mathematical curiosities with no experimental basis. The fastest speed plausibly achievable with foreseeable technology for a meaningful payload is somewhere between 1 and 10% of light speed. At 1%, the journey to Alpha Centauri takes over 400 years. At 10%, roughly 42 years. Neither is easy. The lower end is a generation ship problem. The upper end is a single lifetime problem, but both ends carry the full weight of every other constraint. Now add energy. Accelerating even a modest spacecraft to 10% of light speed requires an energy expenditure comparable to the total annual energy output of a mid-sized industrial nation. For a crewed vessel massing thousands or tens of thousands of tons, the energy requirement escalates to a fraction of the total energy output of human civilization sustained over years. This energy must be generated, stored, or transmitted. None of these tasks has a demonstrated solution at the required scale, and the energy is consumed during acceleration alone. If the mission requires deceleration at the destination, the energy budget roughly doubles, because the spacecraft must either carry enough fuel to slow down, which means it must accelerate the fuel as well, compounding the mass problem, or it must rely on some external mechanism at the destination, where no infrastructure exists and none can be pre-positioned without a prior mission that faces the same constraints. Now add shielding. At any significant fraction of light speed, the interstellar medium becomes a hostile environment. Gas atoms strike the forward surface with energies sufficient to erode material over time. Dust grains impact with energies equivalent to small explosions, cratering and weakening the hull across decades of continuous bombardment. Protection requires a forward shield of substantial thickness and mass. That mass must be accelerated to interstellar speed. It adds to the fuel requirement. It adds to the structural demands. It feeds back into the propulsion and energy problems. Now add radiation. Galactic cosmic rays permeate interstellar space uniformly. They cannot be avoided by choosing a different route. Effective shielding against the highest energy cosmic rays requires meters of dense material or extremely powerful active magnetic fields, both of which add enormous mass and power requirements to the vehicle. Inadequate shielding results in cumulative radiation damage to both biological tissue and electronic systems. For a crewed mission lasting decades, the cancer risk, neurological damage, and cognitive decline associated with chronic cosmic ray exposure are severe. For electronics, the cumulative dose degrades semiconductor performance and increases the rate of single-event upsets. potentially corrupting data and causing system crashes over the course of the journey. Now, add reliability. No complex machine has ever operated continuously without maintenance for the duration required by an interstellar mission. Even the most conservatively designed systems experience component failures on timescales of years to decades. Over a 40-year mission, the cumulative probability of a critical system failure approaches near certainty unless the vehicle is built with levels of redundancy far beyond anything ever achieved. Redundancy adds mass, complexity, and its own failure modes. And every failure that occurs in transit must be handled with onboard resources alone. There is no resupply. There is no rescue. There is no mission control that can intervene in real time, because the communication delay between the ship and Earth is measured in years. Now, add biology. Human bodies evolved for Earth. They require gravity to maintain bone density and muscle mass. They require a specific range of atmospheric pressure, composition, and temperature. They require nutrition that can only be produced through biological processes, agriculture, aquaculture, or synthesized food systems that have never been demonstrated in a fully closed-loop configuration for more than a few years. They require medical care that on Earth relies on an infrastructure of hospitals, pharmaceutical supply chains, and specialist expertise that cannot be replicated on a spacecraft. They are vulnerable to radiation, isolation, confinement, and the psychological effects of knowing that there is no possibility of return, rescue, or communication with anyone outside the ship on any timescale shorter than years. Now add time. Time is the thread that connects every other constraint. Every problem listed above exists because the journey takes too long. If the crossing could be made in hours or days, like a flight between continents, the radiation exposure would be trivial, the dust damage would be negligible, the reliability demands would be ordinary, the life support requirements would be manageable, and the biological and psychological stresses would be tolerable. But the crossing cannot be made in hours or days. At any achievable speed, it takes decades at minimum and centuries at worst. And across those decades or centuries, every risk accumulates, every system degrades, every vulnerability is tested not once but continuously for the entire duration. This is the cumulative wall. Not one barrier, but all of them simultaneously, each one made worse by the others, none of them removable, without altering the fundamental physics of distance, energy, and time. Here is why the cumulative nature of the problem is so important. In most engineering challenges, you can solve problems in sequence. Build a stronger bridge, design a more efficient engine, develop a lighter material. Each solution is independent, and each one brings you measurably closer to the goal. Interstellar travel does not work this way. Solve the propulsion problem, and you still face the shielding problem. Solve the shielding problem, and you have added mass that makes the propulsion problem harder. Solve the radiation problem with massive shielding, and you have increased the energy requirement, which makes the propulsion problem harder still. Reduce the travel time by going faster, and you increase the dust damage per unit of hull area, which increases the shielding requirement, which increases the mass, which requires more energy, which requires more propulsion. The problems form a closed loop. Progress on any one front is consumed by regression on another. The system resists optimization because improving one variable degrades others. And the total difficulty of the system is not the sum of the individual difficulties, it is their product. This distinction is the core of the argument. And it is the distinction that is almost always missing from popular discussions of interstellar travel. A documentary that focuses on propulsion makes the problem look like an engine problem. A paper that focuses on radiation makes it look like a shielding problem. A study that focuses on life support makes it look like a biology problem. Each one, taken alone, feels solvable. Difficult, yes. Perhaps requiring decades or centuries of additional research, yes. But fundamentally within the reach of a sufficiently advanced civilization. The cumulative picture is different. When you hold all the constraints in your mind at once and trace the way they interact and compound, the space within which a solution could exist shrinks to a point that may not contain any viable mission architecture at all. It is important to be precise about what this means and what it does not mean. It does not mean that a mathematical proof of impossibility exists. No one has proven that interstellar travel violates any law of physics in the way that perpetual motion violates thermodynamics. The speed of light is not a barrier to travel below light speed. The energy required, while enormous, is finite. The engineering challenges, while unprecedented, do not individually require physics beyond what is currently known. In the strictest possible sense, interstellar travel is not provably impossible, but provably impossible is not the relevant standard. The relevant standard is practically achievable within known physics, plausible engineering, and civilizational endurance. And by that standard, the case for interstellar travel is far weaker than popular culture suggests. An analogy helps here. Consider the difference between what is permitted and what is achievable. The laws of physics permit a human being to swim across the Pacific Ocean. There is no law of nature that forbids it. The water supports a human body. The distance is finite. The direction is knowable. In the strictest theoretical sense, the crossing is not impossible, but no serious person would call it achievable. The distance is too great. The human body cannot sustain the effort. Fatigue, hypothermia, dehydration, predation, currents, storms, and the sheer passage of time conspire to make the crossing lethal long before it is complete. Each obstacle individually might be survivable. Their combination is not. And no amount of swimming technique, no improvement in stroke efficiency, no motivational breakthrough changes the fundamental calculus. The Pacific is not crossable by a swimmer, not because of one barrier, but because of all of them acting together on a body that was not built for the task. Interstellar travel occupies a similar position. No single law of physics forbids it. The distance is finite. The energy exists in principle. The direction is knowable. But the combination of constraints, energy, mass, time, shielding, radiation, reliability, biology, and institutional endurance acts on our technology and our biology the way the Pacific acts on a swimmer. Each constraint individually might be addressable in isolation. Their simultaneous interaction may not be. And the difference between those two statements, between solvable in isolation and solvable in combination, is the entire argument. This is the distinction that popular science consistently fails to make. A documentary about fusion propulsion can end on an optimistic note because, viewed in isolation, fusion propulsion is merely extremely difficult. A paper on radiation shielding can propose a solution because, viewed in isolation, radiation shielding is a tractable engineering problem. A study of closed-loop life support can identify a research pathway because, viewed in isolation, life support is a solvable biological challenge. But interstellar travel does not present these problems in isolation. It presents them simultaneously, interlocked, each one sensitive to the solutions chosen for the others. And the space of solutions that satisfies all constraints at once may be empty, not provably empty, not mathematically excluded, but practically empty in the same way the Pacific is practically uncrossable by a human body. The physics permits it, the reality may not. Consider 3 levels of ambition. The first is sending a gram-scale robotic probe on a flyby trajectory. the Breakthrough Starshot concept. This is the most achievable version of interstellar travel, and it was placed on indefinite hold after 9 years and less than $5 million of spending, because even the preliminary engineering challenges exceeded what the project could address. A gram-scale probe at 20% of light speed faces dust erosion, communication difficulties over 4 light-years, and the fundamental limitation that a flyby provides only a brief window of data collection with no ability to enter orbit, slow down, or return. It is interstellar travel in the most minimal possible sense, and it remains beyond current capability. The second level is sending a meaningful robotic mission, one capable of decelerating at the destination, entering orbit around a target planet, conducting extended observations, and transmitting detailed data back to Earth. This requires a spacecraft orders of magnitude more massive than a star chip, equipped with a propulsion system capable of both acceleration and deceleration, shielded against decades of interstellar medium bombardment, hardened against cosmic radiation, and built to operate autonomously without maintenance or resupply for the full duration of the mission. No design for such a spacecraft exists. No propulsion system capable of powering it exists. No communication system capable of transmitting useful data over interstellar distances at the required bit rate exists. The gap between current capability and the minimum requirements for such a mission is not a matter of incremental improvement. It is a gap that spans multiple simultaneous revolutions in propulsion, materials, science, autonomous systems, and power generation. The third level is sending human beings. This is what most people mean when they imagine interstellar travel. A crewed vessel carrying a human population to another star, capable of sustaining that population for the duration of the journey, protecting them from radiation and environmental hazards, maintaining their physical and psychological health, and delivering them to a destination where they can survive and potentially establish a permanent presence. This version of interstellar travel requires everything the robotic mission requires, plus a closed-loop life support system that functions for decades or centuries, plus radiation shielding sufficient to protect biological tissue, plus artificial gravity or a medical countermeasure for long-duration weightlessness, plus a social and political structure capable of maintaining cohesion and purpose across multiple generations if the journey exceeds a single human lifetime. Each additional requirement multiplies the total difficulty. Each one adds mass, which adds to the propulsion requirement. Each one adds complexity, which reduces reliability. Each one extends the list of things that must work perfectly for decades, in an environment where perfection has never been achieved for more than a few years at a time. The honest assessment is this: sending a gram-scale probe on a flyby trajectory to the nearest star is extremely difficult and has not been achieved. Sending a meaningful robotic mission to the nearest star is so far beyond current capability that no credible engineering path to it exists. Sending human beings to the nearest star is a challenge so layered, so compounding, so dependent on simultaneous breakthroughs across nearly every field of science and engineering, that it may represent the outer limit of what is physically achievable for a biological civilization operating within known physics. This is what the phrase "may already be impossible" means. It does not mean that a decree has been handed down from the universe forbidding starflight. It means that the combined weight of distance, energy, time, shielding, radiation, reliability, biology, and civilizational continuity may already exceed what beings like us can bear. The walls are not absolute, but they may be high enough that no plausible ladder reaches the top. There is an emotional weight to this conclusion that deserves acknowledgement. For the entire history of our species, the stars have served as a promise that the frontier never ends, that no matter how far we have come, there is always further to go. that the curiosity and ambition that carried us out of Africa, across oceans, to the poles, to the moon, would eventually carry us to other suns. The idea of reaching the stars is woven into our mythology, our literature, our science, and our sense of identity as a species. It is, in a very real way, one of the organizing narratives of human civilization. To confront the possibility that the stars may be permanently beyond our reach is to confront a kind of boundary that our species has never faced before. Every previous frontier was eventually crossed. The Atlantic was crossable. The poles were reachable. The moon was attainable. Each barrier yielded to sufficient effort and ingenuity. The assumption, deeply embedded in our cultural psychology, is that interstellar travel is the next item on the same list. That it will yield the same way when we are ready. But the barriers separating us from the stars are not the same kind of barrier that separated Europe from the Americas. They are not made of distance alone. They are made of physics. They arise from the relationship between the speed of light, the energy density of available fuels, the fragility of biological organisms, the finite lifespan of engineered systems, and the incomprehensible vastness of the vacuum between stars. These are not barriers that cleverness can overcome by finding a secret passage. They are features of the universe itself. And the universe does not owe us a path to the stars simply because we wish for one. This does not mean the future is empty. The solar system itself is vast and rich with possibility. The moons of Jupiter and Saturn, the asteroid belt, the Kuiper belt, even the inner Oort cloud, represent frontiers that could occupy human ambition for thousands of years. A civilization that masters the resources of its own solar system would be extraordinary by any standard, wealthier in energy and material than any society in history, capable of feats that would dwarf everything accomplished in the last 10,000 years. The solar system is not a consolation prize. It is an empire of worlds, hundreds of moons, millions of asteroids, enough material and energy to sustain a civilization of trillions for millennia. It is worth dwelling on this point because the solar system is almost never presented on its own terms. It is always framed as a stepping stone, a way station on the road to the stars, a place to practice before the real journey begins. That framing does it an extraordinary injustice. The solar system contains more accessible resources, more varied environments, and more unexplored territory than most people realize. Mars alone could occupy human ambition for centuries. Its surface area is roughly equivalent to the total land area of Earth. Its geology records billions of years of planetary history that we have barely begun to read. Its subsurface may harbor liquid water and, possibly, microbial life. Terraforming Mars, if it is achievable at all, would be a project spanning millennia, a multi-generational endeavor worthy of the species-level commitment that interstellar travel demands, but far more plausible in its engineering requirements. The asteroid belt contains millions of objects, many of them rich in metals, water ice, and organic compounds. A civilization capable of mining and processing asteroidal material would have access to quantities of iron, nickel, platinum, and rare earth elements that would make every resource constraint on Earth irrelevant. The energy available from a single large metallic asteroid exceeds the total energy humanity has consumed in its entire history. The moons of Jupiter and Saturn represent frontiers as scientifically rich as any exoplanet. Europa, beneath its ice shell, almost certainly harbors a global ocean of liquid water in contact with a rocky seafloor, conditions that on Earth support thriving ecosystems around hydrothermal vents. Enceladus, Saturn's small but active moon, is actively venting water vapor and organic molecules into space from its subsurface ocean. Titan, the largest moon of Saturn, has a thick nitrogen atmosphere, methane lakes, and a complex organic chemistry that is unlike anything else in the known solar system. Each of these worlds represents a scientific frontier that could consume decades of exploration. Beyond the major planets lie the Kuiper Belt and the Oort cloud, regions containing billions of icy bodies extending to roughly 1 light-year from the Sun. These are not interstellar space. They are our space. They belong to our star's gravitational domain. Exploring them would push the boundaries of human capability to their limits without requiring the impossible convergence of breakthroughs that interstellar travel demands. A human civilization that fully inhabited its own solar system, drawing energy from the Sun, mining asteroids, exploring ocean moons, building habitats in the outer reaches, would be unrecognizable to us in its wealth, its capability, and its diversity of experience. It would be a civilization that had conquered not one world, but hundreds. Not one environment, but dozens. It would be, by any measure, a triumph of the species. The tragedy embedded in the interstellar dream is that it makes this triumph feel like a failure. It trains us to see the solar system as a cage rather than an empire, to feel confined rather than liberated, to measure our worth not by what we have accomplished within our reach, but by what we have not accomplished beyond it. That framing is not scientific, it is emotional. And it may be the deepest cost of the interstellar illusion that it blinds us to the extraordinary richness of the domain we actually inhabit, but it is not the stars. And the gap between the solar system and the stars is not a gap that scales, it is a cliff edge. On one side, distances measured in light hours and light days, reachable with propulsion systems that are difficult but not inconceivable. On the other side, distances measured in light years, demanding a convergence of solutions across every domain of science and engineering simultaneously, a convergence that may not be physically achievable. The most unsettling part of this conclusion is not that interstellar travel is difficult. Everyone already knew that. The most unsettling part is the timing. The universe placed the stars at these distances before we existed, before life existed, before the Earth formed. The gaps between star systems are not obstacles that arose in response to our ambition. They are structural features of the cosmos, determined by the physics of stellar formation and galactic dynamics, billions of years before any mind existed to dream of crossing them. The stars were never meant to be a frontier. They were never placed at the edge of our reach as a challenge to be overcome. They are where they are because of gravity, angular momentum, and the distribution of matter in a young galaxy. And they happen to be far enough apart that crossing between them may be beyond the practical capability of any biological civilization that evolves on a planet's surface. This is not a failure of imagination. It is not a failure of ambition. It is a confrontation with the physical structure of the universe at a scale that does not accommodate the assumptions our species has carried since we first looked up. We assumed the stars were the next horizon. They may not be a horizon at all. They may be a boundary. The kind of boundary that exists not because we lack the courage to cross it, but because the crossing requires more than courage, more than ingenuity, more than time. It may require capabilities that lie outside the envelope of what physics permits for creatures made of carbon, powered by chemistry, sustained by biology, and bound by the speed of light. Nothing said here forecloses the possibility of surprises. Physics has surprised us before, and it may do so again. A discovery that changes the energy landscape, a principle of nature not yet identified, a form of propulsion that sidesteps the constraints described in this analysis. Any of these would change the calculation. And the honest position is that we do not know what we do not know. The history of science is full of moments when a firmly established limitation turned out to rest on an incomplete understanding. But hope for a surprise is not the same thing as a plan. And the current state of physics, engineering, and biology does not contain a plan for reaching the stars. It contains ideas, some of them brilliant. It contains calculations, many of them sound. But it does not contain a pathway, a sequence of achievable steps leading from where we are to a spacecraft departing for another star. That pathway does not exist. It has never existed. And the cumulative weight of the constraints described in this analysis suggests that it may not exist within the physics and biology available to beings like us. The stars are beautiful. They are ancient. They are vast beyond comprehension. And they may be permanently, structurally, physically beyond human reach. Not because of one law or one equation or one engineering failure, but because the total architecture of the universe, distance and energy and time and fragility and decay was set in place long before we arrived, and it was never configured to allow crossing. That is the most honest thing that can be said about interstellar travel. Not that it is impossible in the absolute mathematical sense, but that it may already be impossible in every sense that matters. The dream is real, the physics may not permit it, and the universe was under no obligation to make the two compatible. We are here. The stars are there. And the space between may be the final answer to the question of how far beings like us can go.